Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and we're in part 5 of an 11-part mini-series within that larger playlist. Here we're doing Hierarchical Designs, this little mini-series, and we're going to look at contrast within a two-stage hierarchical design. Now, as a reminder, the model is y equals x star beta star plus epsilon, so it is a linear model, and we partitioned it into something for the grand mean, factor A effects, and factor B effects within factor A. So B is nested within A. Now I'd encourage you to review parts 1 and 2 for more details about this model. Epsilon term is normally distributed, mean vector 0, and covariance matrix sigma squared I. Now, estimable functions means that the linear combination of the beta parameters are uniquely estimable, and we represent that by lambda prime beta star. So there's two things to think about when you're doing contrast. One is the design, and two, of course, is the design matrix. So here we have factor A and then factor B nested within factor A. So if we want to compare the factor B levels within a factor A level, that sort of makes sense, right? Because they all have the factor, the level 1 factor A effect, so it makes sense comparing them. But it doesn't make sense comparing factor B levels at different levels of A, right? Because if this is different from factor level, 3 is different than 1, is it because the factor B are different, or is it because there's a difference between factors A, 1, and 2? So it doesn't quite make sense. So notes for contrast for factor B within a factor A level makes sense. And so we can think of it as, this linear combination as this. So for a given I, we take a linear combination of the betas associated with that factor A level, and the sum of these CJ's sums to 0. So it's like a treatment contrast in a sense, but it's for factor B within a level of A. And the lambda in matrix notation or vector notation that we would want is we want all these to be 0 except for this piece associated with these betas, right? So this is mu, and also if you think of this, the first one associated with mu parameter, alpha 1, alpha 2, alpha 3, and then this is the beta 1, beta 2, beta 3, and then these are the next betas, and those are the next betas. So if we want to contrast between these, this is what we would need. But now, we have to figure out, is lambda transpose a part of the row space of our design matrix? And the answer is yes. So you kind of have to remember how this is laid out, and I'd encourage you to go back to part 1 for more details of that. But if we take the first row of this design matrix and multiply it by C1, we get this, and the rest are zeros. If we take the 1 plus nth row and multiply it by C2, we get this. And if we take the 1 plus 2nth row and multiply it by C3, we get this. Now, when we add those, this sums to 0, this sums to 0, and then that's just this linear combination, or this, right? So a linear combination of the row space created this lambda vector. So it is estimable. So this is an estimable function. And so this lambda transpose beta star is equal to this rho transpose x star beta star, right? This lambda has to be a part of the row space, and we just determined that rho that satisfies this is this one, the C1 C2 and C3, and then the rest are zeros. Then that creates it. Now, as mentioned previously, we can't uniquely compare factor B levels between the A levels. Now, there is kind of a weird way that we can do that, and that's if we create what's called side conditions, and that we'll discuss that at the bottom of page 2. Now, whether that's appropriate or not, I'll leave that to you. Contrast for factor A can be conducted, but we have to do it in a unique way. So here are lambda transpose beta star, and so this represents the lambda, and the beta star is this, and we want to compare, a linear combination of these alphas, but we can't do it directly. Now, to compare these, we also have to assume that we're taking the average effect of the betas associated with level 1 of factor A, the average effect of level 2, the average effect of level 3, and then comparing them. And this is the way we would compare the levels of factor A. This is part of the row space. So if we take the first row, divide it by B, in this case it's 3. Probably should have just wrote 3 instead of B. B is the number of levels of factor B, and we know it's 3, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. And then if we take this row times C1 times B, this row times C1 times B, and then we move to the next one. We take this row times C2 divided by 3, and we just repeat that throughout the process. We can reconstruct this lambda vector. Now, so the least squares estimate for this, now it's estimable because we determine there is a row, we can take a linear combination of the row space of X, and it's this one, this structure. So the unique least squares estimate is if we plug in the least squares estimate for beta star. Okay. Now, the row we determined was part of the row space. Now, X beta star tilde, so the least squares estimate, this has to equal my, and we showed that early on in this playlist. But M is equivalent to M beta within alpha. In this design, these perpendicular projection matrices are the same, and I would encourage you to go to part 2 of this mini series for more detail. Also, part 2, M times Y creates the mean vector for factor B within level A. And then this has a very specific structure. So if we take this row, which we determined to be this, it creates a linear combination of the mean of the yi's. So we take the average response of all the observations under, say level 1, and then level 2, and then level 3, and we add them, and then that's how we compare the linear combination for the effects of factor A. Now, the individual parameters are not estimable unless we impose side conditions that they sum to 0, and that the betas, for a given I, they sum to 0. And so I don't have 0 there, and it should be. And so these sum to 0 for a given I. And this is how you would do it. Now, there are some statisticians that believe this is appropriate to do, and there are some statisticians that believe this is not appropriate to do. And so I'm going to leave that to you, but I'm going to show you how to use these to create estimable functions. And so this particular linear combination of the betas, or the parameters, is uniquely estimable with the mean of that ij cell. So this is I and this is j within I is uniquely estimable. And if you think about it, that's just, we just pick off one of the rows of the X matrix and boom, we got it. So that we can, it is part of the row space, so we know it's uniquely estimable. And it's uniquely estimable with the mean of the observations of the ij case. So if we take this case, which is here, and it is uniquely estimable, and we sum it over I and over j, then you know, this becomes AB mu, because that's a constant, but this summed over I is 0, and this summed over j for a given I is 0, so we're left with just this. But this is uniquely estimable with y ij dot bar, but since we're summing over I and j, we put dot dots, and if we divide by how many there are, which is AB divided over, then an estimate for mu is the grand mean. Now to come up with an estimate for the beta, for the beta j parameter within I, if we sum this quantity, which is uniquely estimable by this, sum it over I, then this piece becomes AU, this sums to 0, and then this is constant with regards to I, so it just becomes A beta j within I. Now if we divide A over, we're summing this quantity, which is estimable by this, so we sum in the i's, and then we're dividing by how many I levels there are, which is A. Then this becomes y dot j dot bar. And then if we subtract the mean over, then we get an estimate for that beta parameter, which is this. And then we can do something similar for the alpha parameter. So if we sum this quantity over j, then we get b mu, and then there's b of those, and then for a given I, this is 0. Now divide both sides by b, so we're taking this, which is estimable by this, summing over j, and divide by how many there are, so that becomes yi dot dot bar. And then if we subtract that mean, an estimate of that mean, it's the grand mean, and so that's an estimate of the ith parameter. So with the side conditions, this, you know, a difference between the beta parameters, so the effects of different betas with you know, between the levels of A, is estimable, and it's estimable with the means of those you know, the observations within those cells, or that category. One big note is that when you have missing observations, oh boy, does it make creating estimable functions so difficult. So whenever you have a design of experiments, you know, do your best to you know, to gather all the data. Don't create any little missing cells. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.